So we're going to be looking at implementing binary trees. I should be able to get through this pretty quick today. Just to briefly give you a look at how they might be implemented, we would consider trees in general. If you've got a node, like we have nodes in linked lists, but they're connected to more than one other node. Now, if you define it recursively, you could think about a tree as having other subtrees. If you've got the root pointing to other subtrees. And how you might represent this efficiently in the code would be similar to like linked lists, but we've got a root up at the top labeled A, and it's got a link to the first child of all of its children listed in a linked list like this, B, C, D, E. And so it's only got the one link down to its first child. If you want to get to the other children, because we don't know how many there are in a general tree, we could keep on attaching more children by extending that horizontal linked list. Each of these other nodes in turn could have their own set of children, and each of them only has the one link down to its first child. They're depicting it in figure 18.3 with the first child always listed to the left, and then all the other children extending to the right in the linked list. You can imagine that this would be much more complex to try to program. If we're going to implement trees in general, it would be a lot of work. So there is a simplification to get us started. They show a couple other figures where you've got applications for general trees like file systems, and then we've got examples of binary trees here. The one on the left is an expression tree where you could represent binary operations like adding two numbers together, but then you can also recursively have an operation of two numbers being multiplied together. And nested inside that, we've got two values where B has C subtracted from it. And I think they've got the entire expression of what that would look like if you were to read it, if it was not organized into a binary tree like this. They've got it somewhere in here in the description. There it is. So you can see the parentheses nesting the subtrees. And each operation, we've got two values that it acts on. An operator on the left, or sorry, an operand on the left and another operand on the right. And then for the addition, you can see the parentheses goes around all of that. So that would be the operand, the result of it would be your operand on the right, and then the other value A would be the operand on the left for the addition operator. So each of these addition, subtraction, multiplication, they're binary operators. They take two inputs to perform their calculation. And we could grab input from text files, for example, reading in expressions like this, and then we could create instances of binary trees and populate them with the information from the expression to give them a representation that's very useful in our code, because then we could execute these operations recursively if we wanted to. So it really helps to implement our binary trees recursively, and if we create one helper class, the node class, for just specifically having a left node and a right node for two children at most, this would be a nice simple way to get started with trees. Now that's really relative, because this is going to be one of the more complex things we'll get to program. And the majority of the code comes from figure 18.12, your binary node class. That's where we're going to get started here. So I'm going to type this up. I'm going to leave off some of the other implementations of things for separate videos later. And the first thing we would want to get up and executing without bugs would be to add data into a node and then make sure we could get a really basic example of a binary tree. We could have an instance of it. So we've got this binary tree code down here. Most of the implementations for the methods there are pretty easy because a lot of the work gets done in the node. We just want to be able to print a few like we did with the list. So I'm going to pause, get us started. Okay, so what we have so far is just the BinaryNode class. I'm just doing generic type. We shouldn't have to worry about creating elements of the type, because when we want to have our node be populated with a value that we're interested in, the client code should be taking care of that and passing it in. And also if we want to set the value afterwards, then we can call the setter method set element, and again we're passing in an instance of the type for the client data. The only other thing that might need mentioning would just be, for those of you that are curious about what's going on with constructors here, the first one that has no parameters in the constructor, this would be considered default constructor. I'm using keyword this, which might make you kind of curious if you haven't seen it yet inside Java, is just referring to the current instance that's being created by this constructor. And we're actually calling one of the other constructors. So it's a way of eliminating redundant code when you've got multiple constructors. So we're really calling the second one, and we're passing in the 3 values as null for each of them. So it's just, this first constructor is just creating a node that's got nothing set up for any of the fields. So we might want to do that and then set the values for things later with the setter methods down in the last 3 here. And then of course we need getter methods because we want to start being able to check what values are there, and then what are the left and right nodes for children for our binary node. This is enough to get started. We could go play around with things in the client application, but again, I want to make sure I don't have any errors yet. So I would open up my terminal, compile. We've got BinaryNode, and we're fine. There's really not much difficulty going on here in the code from anything that we've seen so far. This is all really straightforward. So in the application program, let's open that up and then play around with our binary node first. So normally I wouldn't be using the binary node itself inside my client application, because that's really something meant to be used by the binary tree as an internal part of the data structure, where the client really shouldn't have to worry about nodes at all or even understand what those are, just that the binary tree is managing the data in the way we would like it to do for us. So really all I'm doing here is just checking how things are working with the binary node. If you're curious and you want to experiment, you get more comfortable doing debugging when you play around like this with what you're programming. So we want to create a binary node first. Let's test the constructor. We'll create a node. Maybe we'll start off by saying root, because it's just the one node that we're working with, so we're not even attaching any other nodes to it yet. So we'll create a new binary node, and because we've got generic types, what do we want to work with? Well, I've been using capital I integer a lot, so I think I'll stick with that for now. And I think we'll create just store the value 0 to start with, and then we'll have null for left and right child. And then we'll see if we can print that system.out.println root has get element from the root. Okay. Whoops. Let's go compile that. And then java c app.java. And there we go, it stored the value, and then we could play around with it a little more even if we wanted to. So of course this wouldn't be the typical kind of code we would want to see inside our application. But we could create another binary node on the left and the right. Let's do integer value of 1, and then it doesn't have any left or right children either. I might even have a third constructor where I'm only passing in a value for a node to store, and then I wouldn't have to keep retyping null null for the left and right subtrees if I just wanted them to have, you know, a constructor where I only pass in one value. It automatically would set the 2 children to null. That would be nice, in addition to what the textbook has, if I was going to play around some more. I think as it is, I'm not going to be doing a lot of this. And we'll move on to implementing more of the tree, so we could see something like this be a little bit cleaner when we move on. And we go to print the tree, we could just take a look at a couple of the values that it's got. So again, this is just purely for demonstration purposes and to get you more comfortable working with some of the methods that you'd likely see with something that's implemented like a binary node. So if we've got the root, we could get the element, and then maybe we'll just print out the left and right child. And again, the statements that we're actually making in our main program, they won't look that nice. They won't look as nice as the last kind of programs we're working with, our nicely finished data structures, where we could just do add and then print the whole structure after. So again, that's part of the reason why we're implementing data structures. So in our client code, it's going to be really nice to work with that data structure. So let's see, the left child of root let's do root get left, I think it was. Let's double check that. Get left is going to give me back a binary node of the same type. And then with that node, I should be able to get the element from that node as well. So here's another thing you can do. Once you're returned an object, you can continue to go further. And you can think about this almost like nested calls if you wanted to. So this expression would result as the left node that's returned, and that object I could then turn around and call get element from that object. Not the greatest to read code like this, but when you're working with code that's got a lot of hierarchy in the objects, in the structure itself for the data, you're going to see a lot of this kind of thing. Let's do the right. And then of course if there's any issues, I will work through fixing those. If we do Java app, there we go. Your root has 0 and the left child has 1 and the right has 2. So just very low level into the data structure, just working only with the nodes. You can see we would not want to work that way inside our client code. The code is much more difficult to read if we had code written like this. I wouldn't want to work on a project with somebody else where the main application is going into the inner details of a data structure. So after a while, you work on a project, you have lots more source code files, and the ones that are meant to be used to start the program, you shouldn't have to go into the details of some other class like this. And you would want to think more about how to organize your classes and how you're going to use your objects in your project. Hopefully this helps you see the advantages for all of the weird concepts they talk about in Comp 155. So no matter what kind of programming language you're learning, with object-oriented programming, you're probably wondering, like, why is there all these things that are like private and public, and they kind of touch on that a little bit, but then there's not a lot of time to get into practicing it to a level like we do in 251, where we finally start to see, oh, okay, like this is organizing our code nicely, so that then when we go to use our classes inside some other project or program we're working on, that we're not going to have nasty code. So the next thing we're going to do is binary tree. Again, there's not a lot there because it's really just relying on what the node is doing. So I think I'll stop this recording and we'll keep each video short so you can get at exactly what you want and come back to it later if you need to.